Today, let's continue our discussion in difference equation. Before I start, do you have any questions from last time when we discussion? Don't forget to read the book, and also homework 1 is assigned. Homework 1 is due in a week and a half. Please start early on that. If you have any questions on homework problems, feel free to ask me as well. We can discuss that in our synchronized class. Okay, so let's continue with difference equation. So our goal is to solve for a linear constant coefficient difference equation. So here is our original equation. Yn equals to, in general, it is sum k from 1 to n, a sub k, y n subtract k, and we call that system nth order, capital N, nth order. And then I have another sum of all the x, which is the input. So k from 0 to m, b sub k, x and subtract k. Okay. Now this is the nth order system because we have n feedbacks from y. So the goal of the problem is we want to find an explicit expression for yn. In this above equation, everything is in iterative form, or it's in a sum of the input. But I want to know explicitly at time n that you write out an equation, find out the value of y instantaneously. That's what I want. I want to find yn. And in this problem, of course, we emphasize that it is a linear system. And also we have a linear constant coefficient system, constant coefficient difference equation, meaning that these coefficients, a's and the b's, it's a constant. It can be complex numbers, but that's constant. It's not a function of time. It's not a function of n. Okay. So as we did before with differential equation, now everything is difference equation. So we are using n instead of t. We are using n here instead of t. We are using a delay yn subtract k instead of using differential. So you can think that yn corresponding to yt in the differential equation, xn corresponding to xt in differential equation, and then I have yn minus 1 that corresponding to y dot, which is dy dt in the differential equation, y is a function of t. Xn minus 1, which is a delayed input, that corresponding to x dot dx dt in differential equation. Yn minus 2 corresponding to double dot, which is dy dt square in the differential equation. Okay, so if you got all these, then every tool that we used in solving the differential equation can be applied here for the difference equation. Okay, now for difference equation, similarly, we have two parts. One is the homogeneous solution. The other is particular solution. As we said last time, homogeneous solution is the solution of the system itself. So for this part, there is, you can think that as no input xt or xn. That is, everything is due to the evolvement of the system itself. So the homogeneous solution is we are looking at the first part. So this homogeneous solution is we are looking at this part. That is evolving by the system itself. I have this feedback loop. Even though I don't have any inputs, the system will change over time. And then the second part is the particular solution. So here, particular solution yp. This is particularly due to any particular input of xn. So we can think of this as something, it's an effect from this part, from the x, from the second part of my difference equation. Okay. So to solve for the homogeneous solution for the difference equation, the homogeneous difference equation, as we said, that has nothing to do with input. So everything is from the first term of the previous equation. So we put that to the left of the equation. Sum together, sum k from 0 to n, a sub k's, and a y n minus k. On the right-hand side, we have a 0. We don't have any input. As we did for the differential equation, we assume that the solution is in the form of an exponential. Now here we are given without proof, and mathematically we'll find out if I have the equation in this form with a delay yn minus 2, and the solution is unique only in this format, which is a constant base lambda to the power n, and this comes from differential equation 2. Differential equation is we have a y dy dt and y dot or y double dot, and then the solution is that we have a constant base lambda to the power t. So if this is the solution to the homogeneous equation, now the problem is to solve this constant base lambda. We want to find out what is this lambda value. Substituting this in the equation, and then we obtain the polynomial equation. So y equal to lambda to the power n. Substitute. We find out this is the polynomial equation. On the left hand side, we can write this out. It is polynomial, and then we pull lambda n to the power n subtract capital N out of this equation. I just want to make sure in the bracket everything is positive power of lambda. So lambda to the power n plus alpha 1 lambda to the power n minus 1 all the way to alpha n times lambda to the power 0. And we call this part in the parenthesis the characteristic polynomial. Now lambda is a non-zero number. If you can write out a solution like that, lambda is a non-zero number. Therefore, this part we can divide it on both sides of the equation, and we end up with the characteristic polynomial equal to 0. Now, if a polynomial equal to 0, which means we are trying to find the roots. We are trying to find the roots of this polynomial. Those are the zero crossing points. The characteristic polynomial of the system has n roots. If my system is order n, my polynomial, the highest term is lambda to the power n. Therefore, I have n roots, lambda 1, lambda 2, all the way to lambda n. If these n roots are distinct, not any two of them are equal, and those are distinct, the general solution to the homogeneous difference equation is given by that. So y sub hn, simply we just adding all these homogeneous solution roots, the polynomial roots in it, characteristic polynomial roots in it. So lambda 1 to the power n, lambda 2 to the power n, and lambda n to the power n. Then we weight it by different constants, c's, c1, c2, all the way to cn. Where those c's are weighting coefficients, they are the coefficients, they are constant, and they should be determined, and they will be determined by the initial conditions of the system. So now I need to find out those c's. How many I have? I have n of those c's. Right. How many initial conditions I have? Now, what are the initial conditions? We know before is if I am started system at time 0, the initial condition is looking at y negative 1. We mentioned before, this is, you can think of that as a memory memory register of your system. We want to see at time 0, if I starting at time 0, that's the initial time. What is my system? Y negative 1. Now, if my system is order n, then I should have n different memory spots. So I have y negative 1, y negative 2, all the way to y negative n. So indeed, I should have n different values, n different initial conditions. So we can write out n different equations according to those initial conditions, and that will solve for our n unknowns. Those n unknowns are the n c's. In a special case, if the characteristic polynomial contains multiple roots, suppose my polynomial end up with lambda square subtract 2 lambda plus 1 equal to 0, then I know my two roots are lambda 1 equal to lambda 2 equal to 1, because this gives me lambda subtract 1 square equal to 0. And those two are not distinct, and they have a multiplicity. This is one root of multiplicity m equal to 2. If this is the case, we need to write out the homogeneous solution h, excuse me, this is y. Y sub h equal to, I still put all these roots together, c1 lambda 1 to the power n. However, because lambda 1 is a root of multiplicity, so I write out the second term. Second term should be c2 lambda 2n, right? Because lambda 1 and lambda 2, they are equal. Same thing here. So I want to make sure these two terms, they are independent. How to do that? Well, we simply put another time index here. Time index n, and then lambda 2 or lambda 1, they are the same. So lambda 1n. Once you put a time index here, and these two terms, they are independent. So indeed, I can write it out in this form. They'll give me two different c's, and I have two different terms. Otherwise, you can just combine these together. Otherwise, these two adding, because lambda 1 equal to lambda 2, you simply have a lambda c1 plus c2 times lambda 1 to the power n, and then you can write this as c1 prime. So it becomes one term if these two are not independent. Similarly, I write out for the other multiplicities terms, and all I need to do is I'm adding a time term each time. So let's say C3, which is n. Now I already have this term. In order to make those two independent, I put an n square, lambda 1n. And go all the way to Cm, n to the power m minus 1, lambda 1 n. Okay, so these are the roots with multiplicity of m. And then the rest are distinct. So we can write as before. And that is the homogeneous solution of the difference equation. Let's look at an example for that. Say we have a difference equation, yn subtract 3yn minus 1 plus or subtract 4n minus 2 equals to, let's just say 9xn plus 5xn minus 1. We want to find the homogeneous solution of this difference equation. We want to find homogeneous equation. Find this. Okay. Since we are dealing with homogeneous equation, we first set the input equal to 0. So this part goes, it's 0. We're only looking at the equation for order y's. 0. Find the homogeneous solution. We know it is in the format of an exponential. So we have here lambda to the power n. That is the format of my homogeneous solution. We substitute this into my equation that gives me the characteristic equation, which is lambda to the power n subtract 3 lambda to the power n minus 1 subtract 4 lambda n minus 2 equals to 0. and we pull this lambda n minus 2 to the front. We have a lambda square, subtract 3 lambda, subtract 4 equals to 1, equals to 0. And the polynomial equation is in this format. And then we can spread this out. This is lambda times lambda plus 1 times lambda subtract 4 equal to 0. Okay. We find out those two roots. Lambda 1 is -1, lambda 2 is equal to 4. Those are the two roots for my characteristic polynomial. Therefore, my homogeneous solution is in the form of n equal to lambda 1, which is -1 to the power n, has a constant c1. And then I have another term c2 of the basis 4, lambda 2 to the power n. Okay, so that is the solution for the homogeneous solution, for the homogeneous equation. And of course, you want to find out those two parameters, C1 and C2. Now that comes from the initial condition. Since my original difference equation is order of 2, I have here feedback and subtract 2. So this is in the solution homogeneous equation order of 2. Therefore, at the initial time, which is n equal to 0, you have y 0, subtract 3y -1, subtract 4 y -2. This is my equal to 0. That's at the time, initial time n equal to 0. I indeed have two terms here. There are two memory registers of my system. So I have two initial conditions. You have to give me what is y -1 and y -2. And these two has to be known. And those two, you can think that as some already known values, and use that to find C1 and C2. So let's look at what we can do. With this difference equation, we plug in, let me write, we can see that. So we're putting here y0 equals to 3 y -1 plus 4 y -2. Okay. And I also have at time 1 y1 equal to 3 y0 according to the difference equation. Y0 plus 4 y -1. Okay, according to the original difference equation, I can write this. And you can continue to write this y2, y3, y4 in this iterative term. But we only want to solving for two unknowns. So we stop at those two, give those two difference equation with different at a particular time, n equal to 0, n equal to 1. So we can continue this guy with 3 times y0. We plug in from the previous line. So it's 3 y -1 plus 4 y -2 plus 4 times y -1. Now this is equal to, after we find out this is 3 plus 4, so we have 13 y -1 plus 12 y -2. Okay, so given these two, and then we look at my origin with this line, the homogeneous solution I just calculated. Now I have those two, and that should equal to each other, meaning that the homogeneous solution should also work when n equal to 0 and 1. Of course, so from this line, we have yn, n equal to 0. That should be equal to C1 times -1 to the power 0. So that's 1. And C2 times 4 to the power 0. It's also 1. So we got that. And also y1, according to this equation, we have y1 equal to -1, negative C1 plus 4C2. Okay, so these two coming from this homogeneous solution. And these two lines, they coming from my original difference equation. Let me just write out. This is coming from my original difference equation. And that should equal to each other. Okay. So basically, we have here, let me just write out one more. So if these are the same, so 3y negative 1 plus 4y negative 2, that should equal to C1 plus C2. And then we have 13y negative 1 plus 12y negative 2. That should equal to negative C1 plus 4C2. Okay, now because I said y negative 1, y negative 2, those are knowns. Those are the known values. That's just the initial condition. I need to have that when I start a system, when n equal to 0. So these are the knowns, and I can use these two equations, find those unknowns, C1 and C2. So we end up C1 equals to, calculate it, find out this equal to that, y negative 2. And the C2 is equal to 16 over 5, y negative 1, plus 16 over 5, y negative 2. Okay, we're solving for those constants C1 and C2. And then lastly, we just plug that into this format, C1 and C2. We solve for the homogeneous equation and get a very specific output of Y homogeneous solution equal to, you plug these two in, and then we find that. The second part is to find a particular solution of a difference equation. Now, particular solution is due to a specific input signal of xn. So we need to write the entire difference equation. Now, in this time, I have to put in the entire thing. You cannot just remove the first term. It doesn't work because the system is always there. You cannot remove its effect. So we have to work with the entire equation. The good news is that the particular solution always follow the form of your input signal. Let me say that again. The particular solution always follow the form of the input signal. After a while, when n approaching a large number, this particular solution looks like the input signal. Why is that? Well, you can think that the system itself is a transition. It has its transition due to the system, all the coefficients of a's and the feedbacks of y. But after a long while, the system output should be excited or should be the same, similar as my input signal. So this is yn. At the beginning, since from 0 at the beginning, the output will during a transition due to some of the feedback of my system. After a long while, it will be pushed or determined only by the variations of the input, by the variation of the input. Let me give you an example. You still remember something you do for your circuits. If I have a circuit that has some of the a low frequency circuits, and you suddenly give it a high frequency signal, so you will have a transition period, right? The output will have a ramp up, and then you follow that and give you high frequency signals according to the input. Or another example is that if you have a system, you apply your circuitry with a very high voltage. Now the output is not going to jump output suddenly. It will have a ramp up period, and we call that in electronics, we call that a transition period. Due to some of the capacitors, inductors in your circuitry, so you have a transition period. And after a while, you get into a steady state when the output is pushed by the large input. And the steady state here is our output according to the input signal. And so we have, let me just say, you probably have a low voltage at the output Yn, and you suddenly increase the input. I'm not going to jump quickly. So there is a transition period in electronics, and then you reach a steady state, right? This is the transition state, and from here is a steady state or static state. Now this part is due to the things according to the system self, and the steady state is according to the input, that whatever input you give it. So of course, in this case, I will always reach a steady state, meaning that my system is always stable. But for some reason, if your feedback will add infinitely adding together, then your system is unstable. So it's not a story here. You're not going to reach a steady state when your system is unstable. So here, if this is the rule of thumb, it will be very easy to find a particular solution. So if my input signal is a constant, the output signal is also constant. Okay, it does not change as time evolves. When n is large enough, afterwards it just keep a constant. And of course, the value of the constant we don't know. K we do not know. We only know the format. So we still need to using the initial condition to find this value K. If the input signal is a base m to the power n, it's a power term here, and my particular solution will follow that format. It's K times base m, is constant m, to the power n. Now we have the same base m to the power n. The only difference is I have this coefficients here is K. I don't know. I need to solve for that. If the input signal is time index n to the power n in this format, my output will also has time n to the power m, but this is a polynomial. I will have some low order terms here as well, n to the power n minus 1, all the way to n to the power 0. So if your input is a polynomial term with order m, then my particular solution is also a polynomial term with the highest order of m. And these coefficients, k's, are unknown that we need to solve. If the coefficient is time varying, in a sense that the coefficients of this polynomial is time varying, but it's exponential, a to the power n. And then my particular solution is similarly, we have this polynomial, and then we have this common coefficient, which base a to the power n. And lastly, if your input signal is a sine or cosine function, then my output is also a sine or cosine function. So we have here, if this is the input, my output is cosine with the same frequency, omega naught, plus a sine with the same frequency, omega naught. Then I have those two coefficients, k1 and k2, unknown. I need to solve for that. If the input is in a format of sine, and the output is also cosine sine, and we do not know about k1 and k2, but we do know the frequency will be omega naught, follow the input. So this later part is when we look at the input-output signals, they are both real. So you have a real input, you generate a real output. Now, in the case, I can write it as my input is say e to the power j omega naught n to a, right? This is a complex, it's a complex exponential. So you can think that's a sine wave, but it's a complex form. If this is the case, going through the system, and eventually my output will follow the frequency of your input, no matter what I have before. But after the transition period, I will follow the input. So I will have something that has a frequency exactly at omega 0 n. And then the constant is unknown. Constant, like in this case, I have just k. K is a constant here versus a. Now, in this case, because everything is complex, therefore my constant, this k, unknown k, is also a complex number. If it's a complex number, you have two unknowns, the real part, imaginary part, or you have two unknowns, which is the mode and the phase. Therefore, it corresponding to those two unknowns. Indeed, I need to solve for two unknowns anyways if you are dealing with a frequency. Okay. So these are the particular solutions that follow the format of input signal. So finally, we have the total solution of a difference equation. Because difference equation is a linear equation, it's a linear system. Therefore, the total solution is the homogeneous solution plus the particular solution. Okay. Now let's look at an example of that. Let's look at an example for a particular solution. So let me using the same system. So same system is yn subtract 3 yn minus 1 subtract 4 n minus 2. I have some input. So let me just simplify this xn plus 2xn minus 1. Okay. We want to find the total solution of that. We want to find yn. So we already did for the homogeneous solution. So the homogeneous solution, homogeneous solution is hn equals to c1 of negative 1 to the power n plus c2 4 to the power n. And c1, c2 we have already solved previously. And in this case, this is my homogeneous. In this case, let's say I know something about my initial condition, so I want to solve for that. The input sequence xn has a particular format. It is 4 to the power n. Okay, it's an exponential, 4 to the power n. And we want to emphasize this input is causal. So we put a un here. Now remember, un is a step function. It's just simply meaning that I don't have any input when n is less than 0. So un is a function like this. When n is 0, this is n. Greater than or equal to 0, you have a 1. Less than that, you got all zeros. So it's just saying that this signal itself, signal is causal. Y particular n follow the format. So the follow the format is 4 to the power n. Let me also put a un, make sure it's a causal signal as well. Times a k. K is a constant. We don't know. I need to solve for that. But here we have a problem. If you look at the particular solution, we got this term, 4 to the power n. And the homogeneous solution, also we have 4 to the power n. If you write out a total solution, you need to add those two together. So we have this term and this term, they are dependent on each other. They are dependent. And if they are dependent, you can just simply including C2 and K give you only one coefficient. You lost one term here. So as before, for the roots with multiplicity, we also need to make sure this term becomes independent of whatever I have here in the homogeneous solution. Therefore, instead of doing this, I need to put a time unit here. So instead of writing this, I need to write it as K times n, put a time unit here, 4 to the power n, un. Okay, that just to make sure that this term, particular solution, is independent of any terms in my homogeneous solution. Okay, a little trick here. Now, therefore, we substitute this equation, this particular solution, into my original difference equation, the first line. So that is, let me write this out, K n 4 to the power n un subtract 3 kn minus 1 times 4 times n minus 1 un un minus 1 un minus 1. Okay, subtract 4 k n minus 2 4 to the power n minus 2 u n minus 2 equals to the input. Now input, I have this particular format. So I can write this out as 4 to the power n un plus 2 times 4 to the power n minus 1 u n minus 1. Okay, after the calculation, in this case, we have we want to pick up a n greater than equal to 2, because if you don't do that, if you take n equal to 1 or n equal to 0, you got those two terms, and you just simply lost those two terms. You will not be able to find one. So if I'm plugging n equal to 2, so the best I can do is n equal to 2. You can plug in n equal to 2, n equal to 3, n equal to 4 into this equation. It doesn't matter. But the best I can do is n equal to 2. So I don't lose anything on the second term and the third term here. N equal to 2, we find out the k is equal to 6 over 5. After some calculation, you find out k is 6 over 5. Therefore, my solution is C1, negative 1 to the power n, plus C2, 4 to the power n, plus 6 over 5 n times 4 to the power of n. And of course, you can multiply by un, the entire thing, or you can simply indicate that n is greater than equal to 0. It's a causal signal. It's causal output. Okay. Now, if we are here, what we can do is we can use our initial conditions to find C1 and C2. So before we got y0 and y1. As before, we calculate these from this original equation here. Oops. From this original equation here. So we got those two values. This is y, 3y negative 1 plus 4y negative 2. And then I have my term is coming from this x. When n equal to 0, we have x0, which you plug in here in this equation, we find out that's 1. X negative 1, you plug in here because you have this un, it's 0. y1 equal to 3, y0, right? Plus 4, y negative 1, plus when n equal to 1, so you plug in here when n equal to 1. So x1, you plug here, x1 is 4. x0 is 1, so you times 2, 2 plus 4. You got a 6 here. And then I can continue to write this. You just plug in the previous line. We find out 13y minus 1 plus 12y negative 2 plus 9. Okay, so these two are coming from my original equation, coming from here. These are the two that has y1, y negative 1, and y negative 2. And I also have the equation that can come from my solution here. So y0 is c1. When n equal to 0, that's c1 plus c2. N equal to 0, so the third term goes away. y1 is negative c1 plus c2, and adding 24, 6 times 4, over 5. All right. Now we have these two, and as before, we equate these two together, and then we will find out in these two, this is equal to this is equal to that, and we find out the solution for C1 and C2. For C1 and C2. Okay. Another way of calculating this, since we already solved for the homogeneous C1 and C2, the C1 and C2 for the homogeneous equation, that means we solving for the 0 input. X is 0. We're solving for the 0 input. We can calculate. Now we find this is we find once you this is equal to this is equal to this, we find a C1 and a C2. The other method, because I already solved for y is 0 state, 0 input. 0 input, we already solved for that. This is homogeneous solution. So for the 0 input, we got C1 and the C2 is here. You can think that as the C1 and C2 of the 0 input when x and is zeros. They are all zeros, right? We find that. Now what I want to do, I want to find out the C1 and the C2, those two coefficients. I want to find those two coefficients, C1 and C2, for this guy, for 0 state. Okay, that's another method because I know this. Otherwise, you just plug in, you find the total C1 and C2. So for this method, for 0 state is y negative 1 equal to y negative 2 equal to 0. This is 0 state. So let me use another pen. Now I want to focus to solve for this guy. And the other part is already solved. I want to solve for this. So we plug in that C1 plus C2 equal to 1. Okay. And negative C1 plus 4C2. Should I have a 4 here? Oh, yes, sorry, I should have a 4 here. So I'm looking at those two equations. So 4C2 plus 24 over 5. 24 over 5 equal to 9. Okay. Where does that come from? Well, you said it's 0 state. If this is all zeros, this is all 0, 0. So y0 equal to 1. That's a 0 state. If my initially the system is relaxed. So if this is 0, this is 0, and then I have y1 equal to 9. I have y0 equal to 1. That's why what I plug in here, and I plug this in here, then I get this equation, right? So C1 plus C2 equal to 1, negative C1 plus 4C2 plus 24 over 5 equal to 9. This equal to 9. Okay. With that, I solving C1 and C2. Those two equations also give me C1 and C2. This C1 is negative 1 over 25. This C2 is 26 over 5. Then what I have is I have a 0 state answer according to this C1 and C2. This is negative 25 times negative 1 to the power n plus 26 over 25 times 4 to the power n, and plus this particular solution, which is 6 over 5 n times 4 to the power n, when n is greater than or equal to 0. Okay, so this is also another equation that finds the C1 and the C2. That is a 0 state. Now, if we flip back to the previous one, we're solving in this equation, we got a C1 and a C2 in this format, and I didn't write it out, but when I solved for that, I got another term here, okay, for this guy, and this is my zero input solution. So what I need to do is the final solution will be adding those two together. And you can think of that we're adding two different C's together. And that should be exactly the same if I just calculating from this equal to this. This is equal to this, this is equal to that. And you got this two result that should exactly the same as this one. Last part of this is we are looking at we have already solved for the difference equation. We can solve for a system, and then how do I map that? How do I use that to explain the impulse response of a linear time invariant system? So if I have the impulse response Hn, it is equal to the zero state response of the system when the input x is a delta function and the system is initially relaxed. System is initially relaxed. That's the same thing as zero state. So it's a zero state response. We are only looking at y sub zero state response because system is initially relaxed. Initially relaxed meaning that all these are zeros. All these are zeros. And the input is the delta function. Of course, that's the definition of the impulse response. So with that equation, the zero state is given by this difference equation. That's the impulse. When the input is the delta, and then the output is simply this Hn, the zero state is the impulse response. Because if you plug this in, we find out x is delta n, so xn minus k is delta n minus k. They only take one non-zero value when n equals 0. So we when k equal to n, when delta have a delta 0, so indeed we got this part. So we can see that from this equation, and of course that's something we already know. The delta, if you can write this in this convolution sum, then the input is delta, the output is Hn, that is our impulse response. If the excitation is an impulse, so the input, if the excitation is an impulse, the particular solution is 0. Why is that? Well, we just said the output, according to the particular solution, should follow its form after a long while. So the input is a delta, it's an excitation. It only happened a spike at time equal to 0. Afterwards, it just dies out. It's nothing, 0. So eventually, the output will have nothing. You have excitation, but the effect will pass anyways. So eventually, in the long run, you don't have anything. So that is the particular solution is also 0. Since when for all n greater than 0, xn is equal to 0. So we don't have any particular solution. So indeed, the response of the system to an impulse response to an impulse consists only the solution of the homogeneous equation. It only determined by Hn. Okay, and this is, as we've seen before, this is this impulse response. For an nth order linear difference equation, since the solution of the homogeneous equation is in this format, it's just a solution, and we are using all these polynomial roots, lambda k's. And the homogeneous solution is in the format like this, with all these c sub k's we need to solve. Therefore, we know for a linear time invariant system, the impulse response is always in this format, because that's a homogeneous solution. The impulse response should be like a c sub k times a lambda sub k to the power n. It's a power term, it's a polynomial term. And the impulse response always look like that. And next time, we'll give an example to show how to find the impulse response of linear time invariant system directly from a difference equation.